deliveries.
Like you think it'd be creepy to go, as opposed to leaving your stuff like in a hallway of an apartment or something. I don't know.
Although I don't just have stuff. Someone else is in my house. But see, the problem is it'd be really freaky to have a drone flying at you.
Yeah. All the missiles on it.
So
I would still be creeped
I
out by
suppose
drones.
we should actually start talking about what we're supposed to talk about today. So, not to rein in the smart home.
Yeah, it's not drones and pizza.
Well, actually, the smart home will come back to play here. So, we have been playing around with firewall stuff and, you get basic firewall rules, letting traffic in and out and whatnot. So there's some like underlying stuff that's just going on for us, decisions that the firewall's making that kind of has like a history of how we got here today. And then there's some like minor, like, you know, when you go into the advanced button and you're like, what are all of these knobs for kind of thing in most firewalls. So that's actually what we're going to talk about today. And that involves stateful inspection of packets. So we're going to go through like what that is and kind of how we got here and actually why it still sort of matters and is relevant that we might have to tweak stuff. And then we're actually going to try to blow something up. So that's always fun, right? Minor explode. I mean, and by blow it up, it's like, oh, though we can't get to the web page anymore. But we're gonna be excited for it. Pretend there's explosion somewhere. That's how we're gonna do it.
I'll get a soundboard.
So when we're doing networking, what protocol is using states?
TCP.
Yes, TCP. TCP uses states. What are the states that TCP can be in? There's multiple flags inside of TCP. So how about what are the flags inside of TCP? Let's start with that. Yeah, there we go. So we got SYN, we got ACK. There's FIN. Those are the main. Then there's also, what's that?
Reset middle finger.
Yeah, the reset, that's the official middle finger of a firewall. Push. And there's one more weird one.
CWR.
No? Urgent.
Because that can just
Which no one really uses urgent, but we'll come back to that. So with TCP, we can live in like sort of three states. There's like connecting, established, and tear down. And that's really our three states that we can live in. So firewalls should care about this a bunch. Sometimes they don't, though, so it depends on the type of firewall we have. In the case of a lot of consumer firewalls, oh yeah, so here's where, IP packet, there would be the TCP flags in there. I'm not so worried about that. So when we go to establish, like, why do we do this whole, like, why is TCP a thing, I guess, before I go down stateful packet inspection? Why do we care about three-way handshake in general?
Ensure delivery.
What's that?
Ensure delivery.
So we want to ensure delivery of data, so we want to acknowledge that we receive data. That's one reason. Why do we go through this whole build-up process? Like, what's different between TCP and UDP?
UDP just like spews.
Yeah. Like, the first, 3 packets of me sending you data with TCP, is it actually me even sending you any data? No, it's all just like, hello, how are you? I'm fine. This is how much, big my window sizes are. Let's synchronize sequence numbers. There's this whole thing, little dance that goes on before we even start exchanging data. UDP is just like, I'm going to pour a bucket of data on you now. Hope it works out. And that's really about all there is to UDP. So TCP obviously has way more overhead. If you think about, if you want to send like 1 byte of data over TCP, it's going to take you like 6 packets to do it. Whereas with UDP, you just send 1 byte. Away you go, right? So yeah, we've got all these fun little flags in here. So there's the urgent flag is the one weird one. Does anyone know what the urgent flag is for? Or where we use it? Yeah, we really don't. It was like a cool idea, and then ended up being like, assuming we implemented urgent, I would probably run some little thing on my computer to tag every one of my packets with the urgent flag, right? Like, my data is very urgent, right? You need to prioritize my packets over everyone else's. Yeah, so that one, it has a couple weird things it's used for, but it's not really a big deal. So this whole 3-way handshake part. If you remember, back in the networking days, if I want to say something to you or if I want to send data to you, the first thing I do is send a SYN, and what do I expect back from you? I expect a SYN ACK back. So you set both bits in the flag to say SYN and ACK. The other part that we have going on is each side is maintaining their own sequence number. That's something that some people get confused about each time. There's not a sequence number. We each have our own. So I'm tallying when I send packets, so I have a sequence, and you have a sequence, and we do keep track of each other's, but they can be totally different numbers. They just have to be incrementing in order. Why do we do the sequence numbers?
So that you know if you lost a packet.
Yeah, like Oregon Trail, if somebody didn't make it, we want to be able to like request like, I didn't get number 4. Somewhere along the line, something's missing. So that's what we got sequence numbers for. And it also can be, we need to reassemble data structures in order. So that helps a lot too, to make sure we put data together in the right way. Similar to like if you have a puzzle, right? They don't ship the puzzle assembled, right? Because it would be big. They break it up into a million little pieces and throw it in a box. And then you have to figure out the order, except you don't have sequence numbers, so it's really hard. But if you had sequence numbers, it'd be really easy to put the puzzle back together. So, yeah, this is our little dance that we do to set stuff up. So, so I talked about urgent, that's weird. What's push do? No guesses? So, when we do the little dance and set up our three-way handshake, we know each other's window sizes, like, here's how much data I would like to receive. Generally speaking, it's going to be most efficient for us to only send full buckets of data or full buffers. Sometimes, though, we're not going to be able to fill the buffer all the way because if I've got 10 bytes of data and my window size is 3, well, I can't equally divide that out. So sometimes we might have to send a packet half full. So that's what push is for. To be like, just push this one through. So that's when we're pushing data back and forth. That's what push is for. So, and then the urgent is like our, evil kitty that no one uses. So, because it'd be cool if we did have it, but. So, why does the three-way handshake matter for a firewall? For application? Like what could? Verification. Oh, sure. So we want to verify like you're following the rules of networking, right? So that comes down to like, kind of like with software on your computer, we can have software break the rules, right? But there's probably someone like your kernel has protections running on your computer to keep software from deliberately overflowing buffers. Well, some decent kernels do, right? There's protections inside of operating systems, even ghetto things like ASLR, randomizing where stuff's placed in memory, like so you can't guess and just blow up the program. So your software operating systems have methods of like actively guarding against bad things going on. Networks, what's our active protection against you not following the rules? The tubes won't work, right? That's really about it. There's no like traffic cop sitting there enforcing like, thou shall follow the three-way handshake to a T. Because usually like if you don't follow it, you just don't get on the internet, right? Well, come to find out, because of that and because of how network gear is built in such a way that we don't really expect people to do wrong. Because if you do wrong, your data doesn't get from point A to point B. Well, come to find out, if you do the right flavor of wrong, you can actually do a ton of damage. So for firewalls, this is where we get stateful packet inspection. Because normally if we think about like, if I'm a web server and you're someone on the internet and you send a SYN packet to me, you want me to reply, right? Makes total sense. So we have the expected, but then there's the reality. So when we look at a stateless firewall, stateless firewalls just look at IP and port. They don't worry about protocol. They don't look at TCP flags. They just send it on through to whatever device is inside the network. And that's actually a really, really fast way to do it. So they're reading less data of the packet. They have to have less memory to keep track of all of it. And it's pretty awesome. The packet just comes straight on through. Why is that a bad idea, though? Yeah, there's security. So if we come back, like, what could we do that's bad with TCP to a device? So we have a few categories of things that are vulnerable. For what we're going to play with, we're going to use an elite and well-renowned and commonly ran operating system. Very elite, highly regarded OS that everyone will really appreciate. So that's our elite OS we're going to run. We don't see a lot of this anymore, but what kind of devices around now suck at networking? Are there little tiny microcontroller devices around us all the time? So like if you're taking a HVAC system for East Hall, which if you live in this building that much, you'll notice how glorious it is. My office right now is like 76 degrees or something. It's roasting down there. So we're trying to keep the building warm. Well, there's all these fans and everything all across the building, right? So if you are the manufacturer of the HVAC control system, you could build your own like interfacing technology to tell all the fans to turn on, right? You could do that. Or what else could you do? You could say like, hey, Ethernet, that's kind of a thing. I guess it's caught on. Let's just use Ethernet, put a little microcontroller on each fan, and give it an IP address, and boom, can we address everything on our little network for the HVAC? Yeah. What's the problem when manufacturers are doing that? Yeah, so what they're doing is, like, you could take a Raspberry Pi. Raspberry Pi has a really robust, it's running Linux, so it's a hardy device, has a really good network stack, network software built in it. So if you do weird things networking on a Raspberry Pi, are you going to blow it up? No, it's a big enough, it's got enough code in its OS that it's going to be like, yeah, that's not right, and just go about its day. But what's a Raspberry Pi cost? 35, 40, 30, yeah, something like that, 30 bucks. So if you're installing fans, what's a fan cost in like a vent? I actually don't know, 50 bucks, something like that. So do you want to bolt a Raspberry Pi onto your $50 fan? No, because you're going to take your $50 fan, now it's an $80 fan. So what we're going to do instead is, like, well, let's build this tiny little device that's going to cost 75 cents. And we're going to give it enough logic to do IP and Ethernet and receive commands over a network. But that's all the logic we're going to give it. So what happens with that cheap little device when I send a bunch of SYN packets really fast at it? It just blows up. Or even like, there's actually, what are this category of devices called? Not Internet of Things. That's our modern evolution of it, which is just as terrible. SCADA.
Oh, yeah.
These are SCADA systems. So we could be controlling centrifuges if we're enriching uranium, or we could just turn a fan on, right? And there's all sides of it. Nuclear power or turn on a fan. So that's why if you're ever in a pen testing gig where you are playing with or there is a SCADA system, you actually have to be very careful because just port scanning a SCADA controller, you might fry it. Like, they can't handle anything. So now we've took these awful little systems that are plugged into networks all over, and then we said, well, hey, here's a grand idea. Let's now connect it to the internet and call it an Internet of Things, right? So this problem is just getting worse and worse and worse. We've just got all this crap out there that's super, super susceptible to bad stuff going on because people can, send bad data at it. So what we do, at the low level anyway, is implement a stateful firewall. So what a stateful firewall does is sitting in front of our web server, firewall, only stateful this time, when you send a SYN packet to the web server, you're actually negotiating a three-way handshake with the firewall. You negotiate three-way handshake with the firewall kind of is like the bouncer. It sits and like, well, this three-way handshake checks out. We'll send it on, and then the firewall then does a three-way handshake with the web server. So it keeps track of all that stuff going on. So it's, logging all that, making sure that you're not doing something sketchy and trying to protect the innocent little webcam that is about to be popped on the internet or something like that, or protecting the fan controller in the building. So stuff like that. It's tracking all of it. What's the downside to doing this, though? Yeah, we now have the overhead of reading those extra little blocks of memory, which, I mean, we're talking like fractions of a microsecond kind of deal. But when we're talking about volumes of traffic, it actually can add up. What does that do to our hardware cost of the firewall? Costs way more. What do we need in the firewall now? We need more RAM. Because if every session that you generate on a network has to be tracked by your computer, the destination computer, and the firewall sitting in between has to keep a little black book of all the goings on. So you have to have enough memory stored for all that, or to store all of that. So I think this was a question we'd had a while ago of, like, what does the DSU traffic look like? So I just went and pulled the media category off the firewall. So this is a 24-hour period on, what was it? The 17th. So I pulled it a while. RTSP is real-time streaming protocol. So pushing video streams from something. So I don't know what this specifically was because I didn't dive down deeper into it. But it's an assumption that there's some video streaming, Netflix or Amazon or YouTube or whatever, but there's Netflix and YouTube are already in here as categories. And there's something streaming video back and forth. Or it could be online students watching recordings that are hosted at DSU2. I'm not sure. But either, like I'm not going to lie to myself. I know that online students aren't watching 700 gigs every day of online videos now. Not to make fun of our online students. Well, no, I know the online students for our class aren't doing that because these videos are hosted on YouTube. So I actually get stats. And actually, the online students do watch our videos, which is why I'm recording today. But, so if you look at this, the interesting thing, there's huge volumes, and I give props to everyone at DSU for 22 gigs in a day of imager, so that's a lot of cat pictures. So there's that, among a lot of other things. The interesting thing, though, is like if you look at Netflix, 91 gigs is, I mean, that's a lot of data, but it's not that much.
That's surprisingly small.
But
That makes you wonder what the other one is.
What's the big one?
it could be what this
Facebook's
big
gone,
one
YouTube's
is.
gone, and Netflix gone.
My theory on why Netflix is small is Netflix does a ton of compression.
Yeah.
So you cannot, like, you'll have a tough time watching Netflix on a really low-powered device unless it has a H.264 decoding chip on it. Then it does the math to reassemble the video frame. But like when you watch a Netflix video, you're getting a little bit of an image and a bunch of math to reconstruct the image. That's how they compress it down to make it work, because Netflix is fighting with other internet providers to have their own video service. You could
download and watch it later too.
Oh, that could be it too. Yeah.
That thing now.
Yeah. That's a thing now.
So yeah, you can download Netflix videos.
Like a month ago?
The other screenshot I took was
At least
I've never noticed that option.
bandwidth utilization over a period of 7 days. And this isn't total bandwidth. This is just things that are classified as media.
Yeah.
So this is like just media stuff. This isn't all the educational browsing that everyone is doing and all of the research journals that you all download, I'm sure.
Xbox Live.
Yeah, Xbox Live number 2.
Xbox Live.
Didn't quite get a terabyte of Xbox Live in there.
So that's a week?
Yeah, this is over 7 days. Wow. So the other interesting thing is, so when we talk about a stateful firewall then, that meant that just for, actually we'll just go for Steam, there's 986,000 sessions that the firewall had to track. So it kept track of source IP, source port, destination IP, destination port, and it man-in-the-middled, not necessarily man-in-the-middle the data of the traffic, but it man-in-the-middle the three-way handshake for everything coming in and out. So conceptually, this is why you cannot take a stateful firewall that you have in your house and put it DSU. I mean, you're also going to have just the pure bandwidth aspect of it that we're just going to burn it out that way. But the other side of it is your stateful firewall that you maybe have at home does not have enough memory to track all these states. So, and that's usually how that's based. So like pfSense, for example, that we play with, when it builds out its state table, it has a finite number of entries. I think the one I have for the lab today, I think can handle 40,000 states, and that's with a gig of RAM, and it has other things it needs to run. It's not just a gig of states. So what happens in a stateful firewall when you hit that 40,000th state entry in it?
Does it write the storage and then
No.
merge the table?
It doesn't swap. The table is, because this is also a security thing that came up. The state sizes are generally hard-coded. So if you hit that 40,000th entry, then that next SYN packet comes in. We go to store and like, ooh, we don't have any room anymore. So we just drop it. So as soon as your state table is full, you start dropping packets. This was actually a problem. Like you could swap it, but you don't. The state monitoring agent has to run so fast, you don't have time to fetch it from disk. Because if you're man in the middling everyone's TCP traffic, you would instantly slow down your network, which seems silly to like slow it down to the speed of a hard drive. But like if we had to swap everything at DSU even to a solid state, you'd notice. It would be pretty bad with every session you'd go to open up. When stateful firewalls first started coming out, this was a problem. Like a new attack happened because state tables weren't statically sized. We'd just be like, here's a hunk of RAM for the state table. Go about our business. And then some crafty people realized that they weren't hard limited. So as you start filling up a buffer of memory, what happens when it's full? And you add another one. It overflows. So if you have a buffer of memory and you overflow it by a couple bytes, is it a big deal? I mean, conceptually it's a big deal, but does anything really happen? Probably not. No, you have some weird stack stuff going on, but it's going to be fine. Eventually, though, you keep overflowing that buffer, what are you going to run into?
Fun stuff.
Yeah, like something important, right? Whether it's something for the kernel or whatever. So you'd either, I mean, in an ideal world, all you would do is brick the firewall and it would have to reboot. But in a not-so-ideal world, you'd start figuring out how to inject data into the firewall's memory, which is not a good thing. So that's why our state tables are hard-coded with how big they are. So, and that's also why it seems really weird, but like you can go buy RAM upgrade kits for firewalls because they have to keep track of all this stuff. Yeah, it sounds dumb, right? Yeah. But luckily now RAM is so cheap that firewalls just ship with boatloads of RAM in them that it's like you're not going to fill that state table like in the amount of time with the amount of bandwidth that you can run through these interfaces. That's what we have now. It's just, kill it with power, kill it with more RAM than you could ever use. So states are big deal. Keeping track of all of them can cause overhead and slowdowns, but we don't worry about that so much anymore because RAM is cheap and all that good stuff. How about UDP? Does UDP have states? No. Generally, firewalls will keep track of UDP as being like the extra man out there, but it basically just sets like a manual timer of like, we're blasting you with UDP data for a while. So we say, okay, there's a UDP session open. And then eventually when you stop, we're like, oh, this must be closed then. And then we just kind of manually get rid of it. But we still keep an entry so we can see sessions going on even though UDP doesn't really have sessions. So it's just something that you'll see in there. So, yeah, stateless firewalling is faster and way cheaper to do, but we don't want to do it because people blow stuff up. So another thing you could actually do is, it's kind of like in South Dakota, the like South Dakota or Minnesota nice, of when you want to social engineer like a guard somewhere. If you just act like you know what you're doing, the guard's like, oh, what are you doing? Like, oh, I'm going to work. And you just walk by them. They're going to be like, oh, well, they know what they're doing, right? And just go about their business. Hopefully it doesn't happen too many places, but it happens. Like, if you go up and you're confident, you're going to walk by whoever's guarding the door, and they're not going to think anything of it. So this is the thing for firewalls, too. So in stateless firewalls, we're not worrying about the three-way handshake going on. So you could just start sending packets with the ACK flag set on it, and the firewall is just going to be like, oh, well, they've been checked out. Yeah, they're good. They know what's up. So that's a problem. So there's actually a ton of different kind of crazy things you can do with sending bad TCP flags. What's a SYN flood? Yeah. So if, like, ignoring firewalls and stuff like that altogether, if I'm a server sitting here and you send me a SYN, what do I now have to do? Yeah, well, first thing I have to do is write down your sequence number, and then I have to come up with a sequence number, and then put an ACK down, write down your IP address, write down my IP address, and then send the SYN ACK back, right? And then eventually I expect to get another matching one. But I had to write down a little entry in my little black book, right? So what happens if you just overwhelm me? Yeah, eventually I have the same problem that the firewall does. I just get overwhelmed. I'm like, I don't know. We're done here, you know? So SYN floods it's kind of like ping of death. You're not really going to blow up any modern infrastructure kind of stuff with a SYN flood, but you'll probably blow up a internet-connected webcam or a thermostat or a SCADA system with a SYN flood. Like, these are all still things that are out there and that are really fragile and whatnot. So that's what we're going to play with, is actually look in and mess around with a firewall rule. So in the lab, in our most modern operating system in the world, and that's another thing, like if you look at Mac OS or new versions of Windows or Linux kernel, stuff like that, if you start sending a SYN flood at them, we basically have like ramp up mechanisms or timers. So it's normal for you to send me a few SYNs all at once if I'm a website. Because now our browsers make multiple connections at a time. Like when you go to DSU's homepage, we have so much stuff on there, pictures and this and that and the other, that your browser individually tries to request all that stuff at once. If we go back into the modern era of like Netscape Navigator, they would do single sessions at a time. So you'd go to dsu.edu, it would send out a SYN to get the index page, and then it would be like, oh, I need to get an image. Okay, it would close the session and then send out another SYN. And it would just run one session at a time because computers of that day didn't have any memory and couldn't keep track of states, and there's stateless firewalls, all that bad stuff going on. So that era is different now because your browser blasts our web server every time you try to go to our web page because it wants to download stuff as fast as it can, and there's enough bandwidth to do it. Whereas before, when you had a dial-up connection, you weren't going to try to download 2 pictures at once. Like, no, that's verboten. So what we have are basically timers inside of operating systems that say, like, it's normal for an IP address to send us this many SYNs. You know, it's friendly to send so many SYNs within a certain period of time, as opposed to, like, sending them every microsecond or something like that. So I think for the class this morning, I think some of the machines I botched when I deployed them. There was a small meltdown this morning. If you were in networking 1, which you wouldn't be if you're in this class, but if you were in networking 1, I interrupted your test that you were taking this morning by a little bit because I broke something. So what that has yielded is if some of you log into these new VMs and it's showing up like your network adapter's not plugged in, that's not something you've done wrong. I broke something. So that turns this into a watch and demo exercise instead of a play along exercise, because this isn't like a lab you're going to have or anything. So on this workstation, I have pfSense installed. It's running the old skin, but it's the same thing. So we can log in here, and if we go to 172.164.100, we get the most secure web server in the world. Which, guess what this is running on? It is on a stateless firewall on what OS?
Yes, and I.
Windows 2000. Yeah. So come to find out, Windows 2000, Microsoft tried to implement like state protection stuff in it, and they just didn't even come close. It doesn't do anything. Maybe for the bandwidth of like 1997 it worked, but yeah. So we've got this web server sitting here. So, and there's some weird NAT stuff going on with how I had to tweak and create this rule. So if you notice the IP addresses we're going to and stuff are kind of weird, just don't worry about that part of it. That's fine. So we've got our most secure web server in the world. What we can do now is go into Kali. So have you ever heard of someone saying, like, I'm going to ping a port? Like, go ping port 80 on something. It's a weird way to phrase it, but it's something you can sort of do. So when we talk about a normal ping packet, what are you actually sending?
ICMP.
Yeah, you're sending ICMPs. Can you send an ICMP to a TCP port?
Yes.
No. ICMP is like below. It's like you can do TCP, UDP, or ICMP. So ICMP doesn't have port numbers. So when we talk about pinging a port, usually what we mean is sending a SYN and seeing if we get a SYNAC back. Just like when you ping an IP address and you get a reply, when you ping or send a SYN to a port and you get a SYNAC back, what's that telling you?
Port's alive.
Yeah, it's just something there, right? Something's there and something's listening. So in our Kali machine, oh, you guys lose some of the excitement because I did this in the class earlier. So if you're in here, ifconfig eth0 24 220 181 dot, I don't know, 222. Doesn't matter. Configure it with some sort of IP address. Or if it's telling you your interface is unplugged, that's not going to go then. At which point you get an IP address configured. We open up the ever popular Ice Weasel. And here we are, right? The most secure web server in the world, up and running right here. So when you use Nmap, what's Nmap do? It's port scanning. So what's it actually doing?
It's checking for open ports on remote systems. It's not getting information regarding those ports and the services.
So it's checking for open ports on remote systems. How does it do that? Any idea what Nmap's actually doing?
Depends on what you set to do by default. You can do a SYN.
Yeah, so by default it's sending a SYN. So it sends a SYN out, and then it knows if the port is open because it gets a SYNAC back. And then eventually, like if it gets a SYNAC back on port 80, it'll send a GET out to it because it's probably a web server. Gets back like Microsoft IIS 6.0, and it's like, oh, that's a server 2000 box right there. So that's how Nmap is able to start to figure some stuff out for us. Can Nmap break stuff?
Yes.
Yeah. How can you break stuff with Nmap?
Break protocols.
Or you can overwhelm a stateful firewall. So this has actually been you guys know what CCDC is? Competition we run here on campus. Yeah, no idea, right? So a competition running here on campus. We have red teamers that are trying to blow stuff up, and then everyone else trying to protect themselves. So long ago, for those of you that have hung out for CCDC these past few years, it's all been up at the Playhouse. But we used to hold it in East Hall here. So we had a room with like 15 red teamers or something in it. And me being the naive person I am, like, especially go back several years ago, had some random computer with, I don't know, a half a gig of RAM or a gig of RAM or something like that. Very appropriate for a firewall. Like, not a big deal. So had that running, and that was the firewall or the router acting between the red team and all the other teams out on the network. So we threw like 15 red teamers in, and they started doing like the full-on Nmap scan of every single team times every single person times all 65,000 ports. So my firewall, which is sitting there being stateful firewall, quickly had an overwhelming number of states it was trying to track. So all of a sudden the red teamers noticed all their scans are coming up totally blank. Then all of a sudden the red team noticed they didn't have internet anymore. I'm like, well, that's weird, log in. And the firewall is like, no, we're done. Like, the state table is full. You're like, and it actually was bad enough that I had trouble getting to the firewall's interface because the firewall had to open a state or a session for me and do three-way handshake and everything, and they were overwhelming it so much I couldn't even get into the firewall. I couldn't SSH into it or anything like that. So, and then the fix, in the case of pfSense, if you need a bigger state table, you give it more RAM, and then it just automatically grows up bigger. So, yeah, there's actually real-world nasty things you can actually do with Nmap. If you have a stateful firewall that doesn't have enough memory, you can like black out an entire network in pretty short order, actually. So we're going to do that, but not with Nmap. We're going to do a more pointed thing. So there's a tool out there called hping. So hping's pretty sweet. Anyone used hping before? Yeah. So it's like a Nmap is kind of like taking a machete to network scanning. It's a machete approach of like, well, let's just swing really hard and see if we hit something. Whereas like hping is like a scalpel. You're just going to be very an X-Acto knife. You're going to precisely check this and this only. Not that you can't do that with Nmap, but that's what hping will do for us. But we can also go into machete mode with hping too. So, or hping, well, 3. This is still a slightly older version of Kali, but it has hping 3 on it. And with hping, like, you can just do normal ping too. You could do hping google.com and get a reply. Well, not in this VM, but it'll send normal ICMPs. If we do TAC big S, what hping is going to do is send a SYN now instead of ICMP. So we basically turn hping into a port pinger, but it's not really pinging, it's just sending a SYN. And then we have to give it a port 80, saying we're going to, want to ping web server and see if it's open. And then we give it an IP address. So when we do that and you hit enter, it should look like a normal everyday ping. There'll be some different things in there than if you're actually running just the ping utility. But we'll run that. I have my font big. Let's turn this down a little bit. There we go. Alright, so compared to a normal ping, this looks pretty normal. Only instead of getting an echo reply, is usually what ping will say. What it's like, ping is literally saying is, I got a ICMP echo reply. Like, that's literally the packet it got back. So what hping is telling us, well, what is it telling us? TTL of 127. Why is it 127? What is the purpose of the TTL? What's that?
How far it can go before it just dies.
Yeah, like we don't want this packet to just keep traversing the internet forever. We want it to eventually die off. So what it basically can tell us is like how many hops did it take to get back to us. In our case, how many hops did it take to get from web server to us? How many routers? Yeah, it went through 1. So TTL of 128 is the default. It took 1 hop. Life is good. If we keep going, we got our port. What is, and you can actually see the sequence numbers and the window sizes, and then RTT is round trip time. What's the flag's SA? SYNAC, yeah. So we send out a SYN, and it's being like, hey, I got a SYNAC back. So technically, we're SYN flooding this web server right now. Is this like an egregious SYN flood going on? No, we're sending 1 a second, right? Like, I mean, pretty much anything can handle that. I won't say anything, but many things could handle 1 SYN a second. And even in Windows 2000's era, 1 SYN a second was no big deal. Like, you can come in here. Actually, what's cool, if you come in here and start refreshing this web page, you'll notice that your flags that you're getting back, hping's watching them. So you're getting ACKs and pushes, or you're sending out ACK push. in the packet. So nifty stuff going on there. So HPing is a handy tool. If we come over here and go to the home page of pfSense, oh, maybe I did overwhelm it with one a second. Here we go. pfSense keeps track of all the states, and you can actually go view the state table. Right now, we are using 203 out of 47,000 states. So, not really doing much to this firewall. And if you notice, we can come over and browse our very exciting web page. So, the key thing is this particular firewall. Well, pfSense by default is stateful. You can't turn that off inside of pfSense. What you can do is tweak individual rules. So right now the rule I have configured that our firewall's all shipped with is a stateless rule. So if we were truly a stateless firewall, pfSense would have said yeah, there's no states. It's still keeping track of the state table. It's just ignoring it when it comes to the rule. So it's not really it's as close as I could get to getting us a stateless firewall without going through, unnecessary amount of effort. So the other cool thing inside of HPing is we can set intervals, how often to set things out there. And normally you'd say 10 seconds or something like that. If you add a U, any guess what the U stands for? Not unlimited. It's a Greek letter is what it's trying to make. Not micro. Well, it's what it means. But it stands for mu. Remember back from your, I don't know, some awful day in math or something like that? There would have been Greek letter mu. Well, maybe I won't show it. The browser is tired. Please? I don't know, it's just not doing anything. So what if I go to Google? There we go. Watch, I'll have the wrong letter. Yeah, here we go. This is what it's really standing for, is this little U. Right there. So that stands for micro. Tack a 1 on there. Now every microsecond, we're going to send a SYN packet.
Oh.
So the result will be different. So when we start this off, you notice what's instantly not happening now. We're not getting a single reply, right? If we come over to Iceweasel, and if you hit just refresh, it's going to still load a cache version. If you go Control-Shift-R, it will explicitly not use its cache to load the page. So yeah, we've grossly overwhelmed this to the point that it's just yeah, no. I'm assuming already if we go over to pfSense, or even inside of, so I'm going to close the tab, open this up, and try to load this same web server. Don't worry about the IP address. There's weird NAT going on. No, even inside of the network, inside of our firewall here, we can't access it either. So if I refresh this,
Mine eventually came up without refreshing.
did it eventually come up? And you might eventually sneak one in there. We found that I can't even refresh the interface of the firewall. So this is why we would never make a stateless rule facing the real internet, because it doesn't take much. So here we go. State table size, 47,007 out of 47,000. So, yeah.
How did it go over its cap?
It must have some wiggle room or something. I'm not sure.
You have 47,000-ish.
Yeah. So
Sounds computer science.
if we go, that's a very computer sciencey thing. It's about 100%-ish used, right?
It depends.
Yeah, it depends.
That's a crisp one.
So if we look at this actual rule, inside of pfSense and the new skin and stuff has this too. I'm actually going to go stop this because this is getting a little... There we go. We're going to stop that. How many packets in that amount of time we sent?
Oh, God.
908,000 in a period of, it doesn't give me the time, 100% loss, though.
We did it.
So if we scroll down and go into the advanced section of the rules, which there isn't that much we're going to play with down in here, but there's the state type or the state checking I have set to none. So that means we're not enforcing any sort of stateful firewalling with this particular rule. So yeah, there's multiple modes of state checking, right? Why would we have multiple modes? So if we think, this is like something that comes up because every once in a while there is an advanced knob that you need to go tweak a little bit. So we're actually pretty lucky here in the U.S. because like the internet just sort of lives here, right? I mean, not that, but sort of, right? So our connections to stuff, what are we talking about for latency?
Very low.
Very, very low, yeah. We're not usually worried about, any latency really. Are there still high latency connections out there?
Yeah.
Yes. So what these are different, they're literally just timing mechanisms that you can configure. And I guess I, truth be told, don't know the algorithm that they're doing. But what they're doing is there's an assumption of an amount of time. We can assume a certain amount of latency, but there's an assumption that if I receive a SYN from you and I reply with a SYN ACK, that you should be sending me an ACK sometime, right? So that's what these are doing. These are saying, like, there's a ratio of how fast I expect you to be replying to me, and there's also a ratio of how many packets I should be getting from you. If I'm getting, if you go to DSU's webpage, I don't know, there's probably like 30 SYNs that you'll get out of that or so at an instant, so that's a bunch. Should we be getting like 30,000 of them? That would be suspicious, unless there's some bad natting going on somewhere. So that's where these different state types come in. Where would we see like super high latency connections?
Satellite?
So satellite, if you look at, there's just satellite-based internet, right? For rural places, it has decent bandwidth, but high latency. So we can send you a lot of data. It just takes a while to get there, which is kind of a conceptual, like, it's high latency, high bandwidth, if you think about it. But it'd be kind of like it's the exact same of like the 4-lane interstate going into Sioux Falls goes from 85 to 65, right? There's still 4 lanes of width there, but we slowed it down, how long it takes latency to get from 1 mile to the next. So that's a big one. And if you actually look at like Antarctica, are there people there? Yeah, there are.
Oh, yeah.
There's research bases there. Yeah. So unlike Australia, which has a higher latency because, poor folks are in the middle of an island kind of, or middle of nowhere, middle of ocean. They have to go through, before they get to like DSU's homepage, they got to go through a lot of hops. It just takes them a while to get here. If you look at Antarctica, can we put an undersea cable there? No. Glaciers and ice sheets shifting that's not privy to cables being, running under the water and stuff like that. So in Antarctica, their entire like continent is only connected via wireless. So it actually is a satellite uplink that actually I believe comes somewhere down in Colorado for the primary link to Antarctica. So they have a high latency connection there. So there's like, and I doubt like as a firewall admin, you're going to get a call of like someone from Antarctica is trying to get to our website. You should check your NAT configuration, but it's possible that stuff like this does come up when you have folks in latent areas. The other one in South Dakota, it's kind of going away, but we can have like remotely controlled irrigation systems and remotely controlled, just remote accessible farm equipment, more or less. That if it's an older type system, it might have, old systems, you just have to drive out and flip it. So it's a very high latency connection there. But a lot of them are connected with dial-up. So, and there's still, believe it or don't, people with dial-up internet out there. So if we expect everyone to send us an ACK in a certain amount of time and you have dial-up internet, it's going to take you a little bit. So we might actually think that you sent us a bad SYN packet and expire it out. So that's why we have all these different states or state like checking mechanisms. And I think, I don't know, is there someone? Yeah, there's one of these anyway that's really good for, I think it's sloppy. Like the state type that we should use is keep state, but sloppy state I think just loosens the requirements up a little bit. I do like the description of none is do not use. Oh, it says do not use keep track. So anyway, that is stateful firewalling. It's like it's something that oh, here's our hping. Well, actually hping 3. There we go. It's something that's going on inside the firewall, but we never see it going on, generally speaking. Or if you look in your consumer like Linksys router, there you'll see like somewhere in there, and it's probably even disabled by default. It'll be like enable SPI, and that's all it'll say. So generally speaking, a lot of devices disable it because your crappy little home router doesn't have much memory and might be slowing stuff down. Or people look on a forum and say, well, disabling this stateful and this SPI thing makes our router run way faster, so go disable it, right? So big thing to watch for. Weird thing that we can tweak and play with. So going forward, what we're going to start to tinker with, we're not going to go down the wonderful world of NAT just yet. But what we will play with next time is doing like really similar firewalling stuff, only with new firewall platform. So that's kind of the idea is like we've got the concept of we need to make a firewall rule on this interface because the traffic is going over there. This is what the rule needs to look like. So now what we're going to do is take all of this vast knowledge that we got playing with pfSense and say, well, how does it apply to this other vendor or this other brand? Because it's the same thing, it's just a firewall, but it's different. So that's what we have to look forward to. Does anybody have any questions on anything? Nothing? Alrighty. So with that, I will see everybody on Tuesday.